Hey guys, today I'm gonna shoot a video to talk about the questions in practice quiz 2. I did get some problem from email, and I also will cover some of the things that I think I should explain more, and I didn't have time. And other than that, as you can see on the agenda, I'm planning to also cover the two practice problems from the slide. One is the last one from chapter 5. Is the one that asks you to calculate the standard deviation. And the other one is about the very last problem that we covered in class on Wednesday in chapter 6. It's about how the negative covariance will affect portfolio risk or portfolio standard deviation. That's it. And I also invite one of your classmates, Yuran, to give me some feedback when I'm, hey Yuran.
Hi everyone.
When I'm going through the questions, in case I'm too fast or I didn't explain enough. So she might represent some of your confusion, hopefully. Let's get started. So let's first do the practice quiz 2, okay? Oh, not here. Okay, so the first question that I want to talk about is the question 4. So it's the question itself asks you the difference between the empirical return distribution, like stock return distribution, how it differs from the normal distribution. The short answer is just from the slide. I told you that the empirical return distribution has higher tail risk and has some skewness. So tail risk in the term, if I use the terminology, it's called the higher kurtosis. So the answer is A, as in the slide, but some student asked me to explain more what the tail risk is. So let me elaborate it. Let's first see through B, C, and D. So these three are wrong because for normal distribution, it can have any expected value, which is mu, and also can has any standard deviation or variance sigma square. So the high or low mu and high or low sigma square does not change the fact that it is a normal distribution. So B, C, and D are wrong. And higher tail risk, it means, as I said, in the class, if a normal standard distribution, say this one, the red line, if it represents the normal distribution, then in the data, what you observe is the data might look like this. So again, this plot is the PDF, which is probability density function. So just a quick review from your statistic class. When you want to calculate the probability of something, when you're given a PDF, the probability is, for example, you want to calculate the probability, the random variable is from, say here is minus mu minus 1 standard deviation. So the probability between mu minus standard deviation sigma to mu is this whole region. If you have the red PDF probability density function. So the probability itself is not the curve itself, it's the shadow, the area of the shadow region under the curve. So what the tail risk means is that compared to the normal standard deviation, you can see the probability that your return gonna be below, for example, mu minus sigma. It's a little bit tiny. So the shadow region, the areas of the shadow will be bigger if you use the blue dotted PDF, meaning that the probability that your return goes to the very left, the very extreme negative value, will be higher than if you use the standard normal distribution, which again, in the standard normal distribution, the probability will be the shadow, the red shadow area here. So the difference will be in green, this part. Okay. And also the same thing applies to the right-hand side, this side, for example. So say if this is mu plus 1 standard deviation, and if you use the empirical, the blue line, blue PDF, then the probability that your return will be higher than the mu plus sigma will be this blue region all the way to the positive infinite. And the red will be this one. So you can see, compared to the normal distribution, you have higher probability that your return gonna end up with very high or very, very low level. So when we say very high and very low, it means to the two extremes on the from infinite to negative infinite to positive infinite. So this is basically a little bit nerdy or technical way to explain tail risk. Intuitively, what it means is that just compared to normal distribution, you are more likely to end up with very high return and very low return, which might increase the volatility of your portfolio or of your investment. But most importantly is that the realization of extreme case will be more likely than it should be in the normal distribution. This is the tail risk. So that's why we choose A here, because from the data we can see the empirical return distribution has fatter tail, which fatter tail is the green here, and also this excess probability on the right-hand side. So we call it fatter tail or higher tail risk. Do you have a question, Yuran?
No.
Okay, great. Then let's go to question 5. So the question itself is very straightforward. Which of following return is most used to measure long-term performance with a compounding effect? And the answer would be B, the geometric average return. I got a question about C. So in which case we're gonna use the dollar-weighted average return? The example will be, I assume you should learn it from your corporate finance class. And it's called IRR, internal rate of return, another name of it. But I will still give an example. Suppose you, suppose you have a project, like for example, constructing a restaurant, or like building some project that is long-term. And what you need to do is you have to invest some money today, which is at time 0. And the project itself will return you some cash flow, or maybe need some extra investment in the future. Let's say today you have to invest $1. or you can take it as 1 million. Also good. And in 1 year, let's use year horizon on these numbers. So suppose in year 1, the project will give you $0.2 as a return. Okay. And in year 2, for example, it gives you $0.4 as a return. And in year 3, say if you're constructing some restaurant or some building, maybe in the future the project manager come to you and say, hey, we need some maintenance costs, or we need some other costs. So maybe in year 3, you need to invest a little bit more, say $0.5. And in year 4, you finish building the whole thing and you sell it, you liquidate it, for example. You get money back and get all the profit back. Say you sold it for 2 million. Okay, it's very hypothetical, so it can be any real world example. The key thing here is that for the IRR, or the dollar weighted average return, in comparison with the arithmetic average return and the geometric average return, the IRR only has cash flow to get it. In other words, you observe a stream of cash flows, either negative or positive. What you want to do is to back out what the implied rate of return from this cash flow. So in other words, like you have a series of cash flow, and you might want to compare this cash flow with, for example, invest in SP 500, which you know the expected return, and you know like historical performance, you know the return. You want to compare these two things. What you need to do is you have to convert the cash flow to return. Then you can compare this implied return, which is exactly why it's called internal. Okay, implied rate of return. The implied return, you can use it to compare with, for example, S&P 500 or like treasury bill. Then you can say, oh, which project would be better. So usually for IRR, it's not that easy to calculate directly. We don't have closed form solution, but the key of IRR is to make the investment equals to the discounted future cash flow. This is cash flow, CF. So IRR is something that makes them equal. Intuitively, the investment side is your cost, how much you pay today, right? And the discounted future cash flow is your profit, is your revenue. What you want is, you want this internal return, implied return, to make you are not losing or you are not making extra money, just to make the cost and benefit equal to each other. So as a result, we can follow the formula that we covered in class, which is -1, not -1. So if you think about the investment is positive because you pay $1. The cost is $1. It equals to, this is 1 year later, 1 plus ARR, you discount by 1 year. Minus okay. So if you use Excel or use your financial calculator, you are able to back out what is exactly this thing, the return that makes the left-hand side equals to the right-hand side. Why it's called dollar weighted average return? is because this item has a bigger impact on the number of the IRR than the other 3 items. Because the $2 is quite high. But again, this is like not absolute, because the further the cash flow is, like if it's in 30 years or 100 years, because it will be discounted back through many years, its power will be less influential. So there will be a trade-off. But intuitively speaking, the highest cash flow should have more impact than on your number of the return. That's why it is called the dollar-weighted average return. And again, it's just to make the investment and the discounted future benefit equal to each other, so that there is no arbitrage opportunity. And then after getting the IRR, you can compare it with other returns that you know. Okay, I will not solve it here. It's just a hypothetical problem, and I believe you should learn it from the corporate finance class. Any questions?
No.
Good. Okay, let's go to question 7. This is something that I want to cover. So it's very, very straightforward, I think. It's just a yes or no. And I asked if someone calculates the average historical return and claims that he finds the expected value of stock return, is his statement true, right or wrong? So the answer is no, in 2 senses. First one is S&P 500 is not equivalent to stock return, okay? Because S&P 500 is a portfolio, it's an index. It represents the whole stock market, but not exactly stock return. And secondly, in this question, I want to kind of test what I emphasized in class, the difference between population and sample. Again, if you get the average historical return, this is the sample estimate. But expected value should be a population term. I think the answer is very clear why it's no. The reason I bring it up is because usually if you look at like articles or even papers, research papers, people do not really differentiate the population and sample. So for example, in the practice problem in chapter 5, it just asks you to calculate the standard deviation. But in reality, standard deviation, I mean, strictly speaking, standard deviation should be based on the population probability distribution. Like you have to know every state of the world. But usually people just say, okay, I get the standard deviation from the data. And although it should be called the estimate of standard deviation, but people will just call it the standard deviation. I know it's a little bit too like detailed, but the thing I want to emphasize is that you have to understand between the hypothetical term, which is expected value, and the data, there is a gap. But in reality or in practice, people do not always differentiate them. But I hope, like in your mind, in your like background, in your brain, you have a sense or you realize that what is the theoretical assumption term and what is the data. And the data might not be perfectly proxy for the theoretical term, although it's close enough, although people call them the same thing, but they are not actually the same thing. And don't be surprised when you hear someone, especially practitioners or even other researchers, say just use the same thing to describe these two. Okay, that's the thing I want to emphasize on question 7. Do you have a question, Yura?
Yeah, I'm probably still a little blur.
Okay, what's the confusion?
So what you have emphasized, it's basically the difference between population and a sample.
Yeah.
So basically the question, he finds the expected value of the stock return, it refers to like all the stock return, like the population.
Oh, okay. So do you remember in class we said for population, you have to know first all the possible numbers, all the possible values, right?
Yeah.
And second, the probability, exact probability with each value.
Oh yeah, so since we're not able to know all this value, so it is impossible for him to like find the exact stock return.
Expected, exactly.
I see.
So, but as I said, if you use sample to calculate the average, you have a good proxy for what it is, the true one, the exact expected value.
I see, but it's still an estimation.
Yeah, it's still an estimation. It's not the value. It's an estimation.
I see. Yeah, that's
Yeah.
clear.
Okay. Well, again, after your is clear with that, I want to say is that in reality, some people will still call the estimation as expected value. It's very common. So, for example, sometimes in the paper, you can just see people just call the historical estimation as the expected return. That's fine because we have many data and long enough data or enough amount of data. So it should be very close, which is fine. But for some other smaller sample, what I want to say is that although sometimes people claim they find this thing, it's not really strictly speaking, the expected return. It's still an estimation as long as it's from the sample. It's clear, Yuran?
Yes.
Okay. Now let's go to question 9. So investor with higher risk aversion will request higher risk premium with given riskiness, okay, not lower. And yeah, I think C is very clear. Higher riskiness is not possible because the investor is risk averse. So why higher risk aversion will lead to higher risk premium? Let me remind you what is risk premium. It is, if we use stock as an example, it will be expected return on the stock minus the risk-free rate. Okay, so it's basically how much higher the expected return of the stock should be than the risk-free rate. Why this is higher when the risk aversion is higher? The short answer is you should view this thing as a reward for taking risk. So it's like for example, you're gonna take the exam, and the exam score will be the reward for your effort. The higher effort you put, the higher score you're expecting, right? Similar here, like for risk-averse people, when they invest in the risky asset, they're actually making something like the effort, or they are sacrificing something. So what they want is they want higher reward to compensate for their risk-taking behavior, which they don't like, to compensate for their dislike toward the risk. So the reward should be higher if the risk aversion is higher. This is the very simple intuition. Why that's the case? There is a mechanism underlying it. So again, because RF is just some constant number, it doesn't matter. What changes is this term, is the expected return on stock. Expected return is expected next period price divided by this period price. Okay. And maybe -1 because it's a net return. So when some investor is risk averse, what is changing is the denominator. Because the expectation of the future price is just expectation. It's something you can think it as common knowledge. Suppose you know all the possible future state and all the possible probability and all the possible value of the PT1 next period price. So this term, you can think it as kind of constant or just a value. But today, investors' behavior will have impact on this term, the current price. Why? Because if the investor demand is very high, the current price will be higher if demand is high. So think about it, when many investors rush in to buy the GameStop, the price goes up because there is more demand, right? And of course, it will go down if the demand is low. Then here's the thing. If the investor is very risk averse, he or she does not want the risky stock, does want to hold the risky asset unless the price is low enough, right? If the price is very high, meaning you cannot get a lot of return, you cannot get a lot of expected RE out of it. So you think, the reward is not that good for me to take the risk. So if you're risk averse, you don't want to buy it until, because if everyone don't want to buy it, the demand is low, the price will go down until some point that most investors will think, oh, the price is quite low already. So the expected return from the price, from holding the stock, is high enough for me to take the risk. I'm happy to do that. So people rush in, people go to buy the stock, and then there is some stable price, which is what you observe today on the market, like the price of some stock, which balances the demand, like high demand and low demand, until some point that there is enough investors come in to buy the stock, so that the expected return will be stable. Or think about it from another perspective. If the whole market is full of very high risk averse investors, all of them are very risk averse. So everyone is very hesitant to buy the stock today. What's gonna happen is, as I said, the price will be low than the scenario that the whole market is full of gamblers, right? If the market is full of gamblers, the price will be higher because people like it, the demand is higher. So for the risk averse scenario, PT will be lower than the risk taking scenario, PT. As a result, because the expected return or the risk premium is inversely related with PT price today. So the premium today will be higher than the premium than the risk-taking investors. Do you have questions, Yuran?
On what's that words below premium?
Oh, you mean this one?
Yes.
Risk
Right.
averse.
The other one is risk seeking.
Risk seeking or risk taking.
Okay.
Do you have a question?
No.
Okay. Although I went very far, like in this question, the intuitive answer would be the more risk averse the person is, the higher reward the person will want by taking the risk. So the risk premium is measuring the reward. Okay, then let's go to question 11. This one I want to cover. So the question is directly from the slide. The Sharpe ratio is used to quantify increasing reward, rank portfolios, measure the price of risk. So there are two things I want to explain more here. The first one is measure the risk. So the invention of Sharpe ratio is trying to quantify the risk and the return. So before someone bring up this terminology, Sharpe ratio, what was happening was that investors only have an intuition that, oh, stock market is riskier, and the maybe bond market is less risky. So it's very rough. It's very intuitive, but not on number. So I know many people don't like math, but sometimes if you quantify some terms, then you're able to rank them. You're able to make a decision rather than just vaguely or roughly know what's going on. That's the reason why people start to use this kind of like Sharpe ratio, coefficient of risk aversion. So they try to quantify things to get a specific number so that they can make a decision. Although the number might be wrong, but it's a good way to proxy what is going on in the world. And that's also the reason why finance these days is getting more and more quantitative to quantify everything and to make sure you can compare between different choices. That's one takeaway that I want to talk about, the quantify. This is very big picture thing. And the second thing is I want to elaborate more on what is Sharpe ratio. Equals to expected return minus risk-free rate divided by the standard deviation. So as I said in the previous question, question 9, the numerator, you can think of it as a reward. My writing is terrible. Okay, so the expected value is some reward in your mind or in your expectation. And the numerator is the risk. So it's the way people use to measure the portfolio risk. And the higher Sharpe ratio, means for a given risk level, suppose you have two portfolios. The portfolio 1 gives you standard deviation 10%. Okay. The portfolio 2 also gives you 10% standard deviation. But for portfolio 1, the numerator or the reward is 5%, while for portfolio 2 is 10%. If you calculate the Sharpe ratio here, Sharpe ratio 1 would be 0.5, right? Sharpe ratio 2 will be 1. So again, because you quantify the reward and risk trade-off, you can see the Sharpe ratio 2 is higher than Sharpe ratio 1, meaning the portfolio 2 has higher reward for the same risk level. Here, especially, the portfolio 1, portfolio 2 have same risk level because they both have standard deviation of 10%. But the expected return on portfolio 2 is 10%, and which is higher than the return on portfolio 1. In other words, for the same amount of risk that you are taking, you get more reward from portfolio 2, which means the reward and risk trade-off is better if you hold portfolio 2. So this is basically what the Sharpe ratio is used to capture or to measure. It's about how much you get when you take some risk. Is that clear?
Yes.
Great. Then last one I want to cover is question 12. Knowing the formula for standard deviation is not enough for measuring the risk of all stocks. Why? So I remember in class, Asim also asked me this question, and I explained these two because we don't know the probability of the state of the world, and we don't know the return in each state of world. It's basically similar as our discussion on population and estimation. These first two, like A and B, are especially problematic when you try to capture the risk of individual stocks. So again, the question here is asking you about measure the risk of all stocks. Okay, it's definitely not enough as if you only know the standard deviation. Like you can say maybe you know how to calculate the standard deviation. You can measure the risk of a portfolio, which includes a lot of stocks. That's fair. You can say, well, roughly, you know, it's a good estimate. Okay, I think I can take it. I can accept it. But if you say, okay, I'm gonna use the standard deviation to measure the risk of all the individual stocks, then that will be wrong. The reason is something that we didn't cover in class yet, but I can give you a first preview. For individual stocks, we use some model called CAPM. CAPM, let's use RI as the individual stock return. It equals to so someone created this model to decompose individual stock return. Let me explain what they are. This RM is the market return. Think about this as the index that includes all the stocks, that you create the index that represents the whole stock market. Okay, this is the one portfolio, RM. And the beta is the loading on the stock, the market stock, the market portfolio. So if beta is very high, it means when the stock, say for example, if beta is 1.5, it means if the stock market return goes up 1%, your individual stock return will go up 1.5%. If the market goes down 1%, your individual stock will go down 1.5%. But if the beta is very, let me use another color, it's very low, say 0.5, it means if the market goes up 1%, your individual stock return will only go up 0.5%. But if the stock on the other way around, it will go down 0.5%. So you can see the beta will measure how the individual stock responds to the market change. If market change a little bit and stock change a lot, we call this stock risky. If the market change a lot and the stock doesn't change a lot, actually, which is the low beta case, we call it less risky. The key takeaway is that for individual stock, we use this beta to measure the risk, not its volatility or standard deviation. Why? Because for individual stock, investors don't care about their individual standard deviation. Why they don't care? Please wait for the later chapter. I'm gonna explain to you why this does not matter for individual stock. The only thing matters is the market volatility rather than the individual stock volatility. But just to let you know for now is that standard deviation of individual stock does not matter. What matters is how it changes or co-moves with the stock market. And that is called beta here. That's why knowing the formula for standard deviation is not enough for measuring individual stock risk. Is that clear for you, Yuran?
Yeah, but hold on. So what?
Are you confused with many things, so you don't know which to ask?
No, I'm just thinking about the logic of this question and the answers. So basically, the formula for standard deviation is the beta. The formula of the
CAPM
is what we use to measure individual stocks, right?
Yeah.
And then why isn't the reason that the formula for standard deviation is not enough for measuring the risk of all stock is only because that you said that we're not able to know all the values of the stocks?
Okay. So for the risk, what we already learned is measure the portfolio risk, right? In class, the standard deviation. So usually we use standard deviation to capture the portfolio risk.
Okay.
But portfolio risk is not the risk of all stocks. Sometimes people want to know individual stock, for example, Apple, for example, Google, just a specific firm, specific stock, what is the risk? Then you cannot use the standard deviation. And what you use is what I just described. You have to use the CAPM model, which we didn't talk about. We will talk about later. The key takeaway of this question is that is to remind you that to use standard deviation, you can only use it for portfolio risk, not for stock, like not for all the stocks.
So portfolio risk and the stock risk are the two things.
Yeah, exactly.
Okay, I see.
Yeah. So again, portfolio consists of many stocks, right? But one stock is just one stock. So you cannot think them as the same thing. They are different.
Okay. Okay, that's clear.
Okay. Then I'm done with the practice quiz 2. And I think most of them I already covered in class, and the numerical questions I think are pretty straightforward. The formulas are all here and numbers are all here. So good luck with it. And let's go to the next one, which is, let's go to the last practice problem from chapter 5. It's here. So, well, I made a mistake in class. I even don't remember the formula for standard deviation using sample standard deviation. Just to recap, we need first to know the sample variance, which is suppose you have n returns. The formula is like this. Okay. So what I messed up is here. It should be n-1, not n. I even told you why it's n-1 to correct the bias, but I myself forgot when I didn't see the formula. So the R bar here is 1 minus n, just the average. For here is just a 1/3, negative 15% plus 35% plus 40%. It equals to 20%, the average. And then we can get the variance, which is 1 over, again, n equals to 3. So 1 over 3 minus 1. And inside we have minus 15%, negative 15% minus 20% squared plus 35% minus 20% squared plus 40% minus 20% squared. Okay. So yeah, let me see what's this number. I only get the standard deviation. Yeah, so this number is around 0.09247, something like this. And for the standard deviation, it's just the squared root of everything above. It equals to 30.41%. So the right answer is B. Why do I use this number? Okay. I think the formula is quite straightforward, but this is related to one of the practice question we covered in practice quiz 2. Here, the question asks you to calculate the standard deviation of this. So the most rigorous way to say that it should be, what is the sample or estimate standard deviation of the returns? Then you should plug in this formula. Because, I mean, rigorously, strictly speaking, when someone asks you standard deviation, he or she should give you all the probabilities of the state of the world, like all the probabilities. But here it's not given because in practice, sometimes people just call the sample estimate directly as the standard deviation, or just call the sample estimate directly as the expected value. That's okay, but you have to keep in mind that the sample is just a proxy, and the sample has its sample formula sheet to do that. Question?
No.
Good. Then let's go to slide 6, right? We are going to finish this one. Let's start with the last practice problem we did in class. So suppose you construct a portfolio with 2 risky assets. How can negative covariance between the 2 risky assets affect your portfolio performance compared to individual assets? Let's look at A and B because it's very confusing. And I remember in class, Nate asked about the return, why the return is higher or lower. So I think you might think there's an effect on return because of the problem, the example I gave you. So here, the portfolio example 1, right? Portfolio example 1 has negative covariance. So you can construct a portfolio which has half investment in one stock and half in the other one, and you can get a constant expected return. Okay. And then here in slide 28, I show you the annual geometric return is higher than either of them. Before elaborate more, let's see the other example I gave you. Portfolio example 2, they have positive covariance, right? They move around together. And again, the annual geometric return of the portfolio is lower than ABC, higher than BCD. I guess that's why some of you might think it has an effect on the expected return, but the answer is no, because this is geometric return. This is not expected return. So very simple, expected return of a portfolio. Here, for example, this one, you have 2 risky assets equals to this one is the expected return of ABC. This one is the expected return of CBA. And this is the weight. For example, here is 50%. And this is the weight on CBA, which is also 50% in our example. So expected return, or in the data, you can think of it as average return, arithmetic average return. It's some number that's different from the geometric return. And also it's some number already given when you construct the portfolio. So think about this. You know the time series of the ABC from 2007 to 2018. What's the expected return on ABC? Is average, just a simple average of this. I didn't understand them. My Google is saying something. It's just a simple average of all of these numbers. This is, you can use this to approximate the expected return of ABC. It's not. I didn't understand that. It's not the same as the geometric return, because this one is just a simple average. So from 2.58 plus 32.1 all the way plus 18 divided by 12 because they are 12 years. And similarly, you can do this one to get the expected return for BCD. Then what your portfolio return will be is simply just the 50% times ABC expected return plus 50% times CBA expected return. It has nothing to do with the volatility because these two items are just a simple average arithmetic return. And the weight are just how you split your money. It doesn't matter with the volatility or the standard deviation. As a result, the negative coefficient, covariance between the two risky assets has nothing to do with your portfolio expected return because there is no covariance term. Okay, so this is for A and B. Let's see C. For C, it asks about Sharpe ratio. Sharpe ratio equals to the expected portfolio return minus risk-free rate if there is one, divided by the standard deviation of the portfolio. Then, because D is right, it can decrease the portfolio standard deviation, so it can increase the Sharpe ratio because this term is mostly depending on the expected returns. Okay. Let me elaborate a little bit more on the, let me add one more page. How can I add one more page?
You can click the
Which one?
square. There's a do you see the
This one?
yeah.
Ah, add
Yeah.
page. Okay, good. So this is a little bit related to the future slides, but let me elaborate a little bit here. This is the plane we used in class, right? Again, to recap, in this whole portfolio theory, you define a portfolio using its standard deviation, which is sigma on the x-axis, and the expected return on the y-axis. So if we have ABC here, what this dot means is that you have expected return of ABC and the standard deviation of ABC. And you have a CBA here. It corresponds to the standard deviation of CBA and expected return of CBA. Okay. These are just the two portfolio that is visualized using this chart. So I can tell you how the covariance will affect it, but there will be some a little bit more mathematics underlying going on. So I will not talk about the math. I will just tell you the result. Okay. If your ABC and CBA co-moves perfectly, like ABC go up, CBA go up the same, like same standard deviation, like just a perfectly co-move, perfectly positive correlated, you're gonna have this one. So what does this line mean? It means suppose you have 50% in ABC and 50% in CBA. So because 50% in your portfolio has 50% in ABC and 50% in CBA, what's gonna happen is that your portfolio expected return will be 50% of ABC plus 50% of CBA, okay? On the y-axis, it's gonna be in the middle because it's just a half and a half, okay? So this is your portfolio expected return. The question is, what is your portfolio standard deviation or portfolio sigma? Portfolio sigma will be here if ABC and CBA perfectly correlated. So the correlation is something we didn't introduce yet, but you can think about it as perfectly covariance or perfectly co-moves with each other. In other words, you cannot decrease your portfolio standard deviation, portfolio risk. This might sound a little bit abstract. Let me give you a comparison. Suppose A and B are negatively correlated. They are moving oppositely, okay? Then what you will get will be, again, your expected portfolio return does not change because this does not change, this does not change, and 50% does not change, 50% does not change. But your sigma P will be changed if negatively covariance. So it will go to somewhere here, for example. So I will explain more about what a curve is in the future. But just to think about this specific portfolio P, your standard deviation P will be to the much more left on the chart than this blue sigma P. The only difference between blue sigma P and the green sigma P is the covariance between ABC and CBA. In blue sigma P, it's positive covariance and even perfectly covariance, like perfectly correlated. So just think of it as positive, for example. But here, the green one is negative. So you can see how the covariance changes the result. Given the same expected portfolio return, remember this y-axis line never changed throughout our discussion. But the risk level goes from here, blue one, to the green one. So the risk level decreased a lot, simply because of the negative covariance. So it also, of course, it increases your Sharpe ratio because your risk, for the same amount of reward, your risk level decreased a lot. And this is due to the negative covariance. So especially in the choice D, it decreased the portfolio standard deviation compared to individual stock because, again, there is some math underlying going on, but the result is that this sigma P might be lower than any of the sigma ABC and sigma CBA. So if you only compare the risk level, so this green portfolio has the lowest risk among ABC and CBA. So it's even less risky than individual assets. Did you catch it, Yuran?
Yes.
Great. So this is just some hypothetical illustration, and we will talk a little bit more about it in the future. But it's all about how the return and the standard deviation trade-off changes when the covariance changes. So the last thing I want to talk about is this one. This one. Which of the following is used as risk-free rate? So I had a discussion on this topic with Asim in class. So originally here, there is one option, one choice is T-bond yield. And obviously he was not convinced in class, because he said, well, I learned in another finance class and says, usually you have to, it depends. Sometimes you need to use treasury bond yield, because if you're analyzing, say, longer term horizon projects or stocks, you should match the maturity using treasury bond. And I also, after class, I also Googled a little bit, and it seems like even Google says you should use treasury bond. But again, my opinion is it depends, because in my own research, also my advisor, one of my research is to analyze the return, stock return at 1 year horizon, like yearly horizon. Yearly horizon is actually not treasury bill anymore, because treasury bill is usually less than 3 months, right? And there should be some 1 year treasury bond correlated with it, but we don't use it. What we do is we aggregate monthly treasury bill to annual frequency. So for example, if I have the return from January to December, what I do is for the annual risk-free rate, I use R minus, like return in January plus 1 raw return in January times raw return in February. Not plus. This is not plus. So times all the way to 1 plus December. This whole thing equals to 1 plus annual. So each of this R, we use monthly treasury bill return. There is a reason, because if you remember in chapter 5, here, yeah, you can see the historical standard deviation and average return. The treasury bonds is actually very high. It's all annualized. The treasury bond is actually very high. Higher return, higher standard deviation. So there is even some research find that if you use the treasury bond for the risk-free rate, the risk premium that is well documented in the literature does not really exist. So it's really weak, but intuitively stock premium, it exists. I mean, there is a much higher return by holding stock. So that's one of the reasons that we use treasury bill, even for longer horizon. We just aggregate to longer horizon, because we believe it captures the real risk-free return, and it's the lowest one, only captures the time value of money. And the reason why the treasury bond is very volatile, it comes from the duration risk or maturity risk. Like longer horizon, there are some, it's just called duration risk happening in the middle. So the return on the treasury bond yield does not really capture I mean, does not only capture the time value of money. There's something going on. And the term structure, which is another terminology you might not know, it fluctuates over time. So the bottom line is that treasury bond fluctuates much more because of the longer horizon. So sometimes we don't use it for measuring treasury risk-free rate because of this long horizon. Another reason, I just talk about long horizon. And another reason is that usually for stock analysis, we don't analyze very long horizon. So for sure, usually because stock is very liquid, most stocks you can just buy and sell on the market immediately. So if you do that, I mean, if you analyze a stock, people don't analyze one stock over like 30 years, 50 years, that long horizon, because it's very short term. So we usually use a higher frequency data, say at monthly frequency or at most quarterly frequency. So usually lower than 1 year horizon. I believe like maybe 90 or even more % of time. Because it's lower than 1 year, we use treasury bill. We don't use treasury bond. Okay. That's another reason. And sometimes even some people analyze stock at millisecond, like the high frequency trading or the like minute horizon. That's also very common to see nowadays. So the short-term analysis, that is another reason. But I agree that sometimes you can use the treasury bond yield, especially when you are analyzing some investment, say for more than 1 year, and you don't plan to take your money out for the whole horizon. For example, you're analyzing a stock for 30 years, and you invest in, you want to compare with the bond, like treasury bond option. What you can do is that you take the treasury bond yield for 30 years, but in this case, you're assuming that when you put the money in the stock, you will not touch it for 30 years to make it comparable. If you touch it in the middle, the horizon does not match anymore. So that's one possibility that you might want to use the treasury bond because you don't want to liquidate in the middle. You just lock your money over there. So that bond might be another comparison. And another reason why treasury bond is also okay is because this risk-free rate, most of time is talking about default risk. So, well, roughly speaking, if a product does not have any default risk, then it's fine. So because treasury bond and treasury bill are both backed by the US government. So US government does not bankrupt, hopefully. We assume the US does not bankrupt. So either treasury bill or treasury bond are free of default risk. That's okay. So within that definition, you can use the treasury bond to refer to risk-free rate because it means free of default risk. So also in that case, treasury bond or treasury bill, either is fine. But I agree there might be some ambiguity going on. And in reality, sometimes people use treasury bill, sometimes people use treasury bond. And especially in my own research, I use treasury bill. I don't use treasury bond. So might be some ambiguity going on in the middle. So if I give you the question, I'm gonna make sure this does not exist. Like here, the corporate bond yield and the commercial paper yield both includes potential default on the firm. So they too cannot, of course, use as risk-free rate. And of course, the D will be wrong. Is that clear for you, Yuran?
Yes.
Great. This is all I want to cover for today. And next time we're gonna start talking about the, oh, where is it? Too risky, I said we did this one. Yeah, Now, from Monday, we're gonna start the statistical detour, which people don't like. But we already covered many of the basic ideas, the covariance, and I will talk a little bit about the correlation. And that's all the statistical term you need to know for at least this chapter. And I'm happy I hope you can enjoy it. And also one last thing for the quiz, I put a test quiz online. It is just a very simple question. 1 + 1 equals to what? 1 × 1 equals to what? It's only for you to test the Lockdown browser if you have never used it. So I hope we can save some time on Monday for our quiz. And it's gonna be great if you can test your Lockdown browser before you come to class, so that we can make everyone's life much easier. And that's it for today. Thank you for coming, Yuran, and thank you for your questions.
Thank you.